Topics in the Theory of Polynomial Functions, Part 1. This is Section 3.6, and I will be following along with your class PowerPoint. So as we start looking at these functions that generally will have powers of 3 or higher on the leading term, the first observation we want to make is the most fundamental definition that ensures us having a zero. It's called the intermediate value theorem. So, intermediate value theorem. The idea is that with these polynomials, we continue to care about when zeros occur. Zeros, also known as x-intercepts, also known as roots, or when the polynomial itself has been set equal to 0 and then solved. All of these things mean the same thing. The most basic type of zero is one that actually has the polynomial passing entirely through the x-axis. And this is where the intermediate value theorem comes into play. So here's a little sketch of a function where you can see here, where I'm drawing the arrow, that the function is crossing completely through the x-axis. The intermediate value theorem basically points out that for this type of zero, we can be assured that we actually cross this height of 0, or we actually have this 0, if, when looking around this point that I'm showing you on the picture, when looking around this at the output, we see a change in sign. Like, for example, here, my y, my function output, is positive up here above the axis, and down here below the x-axis we're seeing that it would be negative. So the idea is, if I plug in some x value, let's call it a, and I plug in, I'll make a be on this side over here, and I plug in some other x value that we'll call b, if there is a sign change between these two, if there's a sign change between the output or the y that I'm getting when substituting in these two different x's, I am guaranteed that my equation has passed through the x-axis. We know there's other types of zeros that we'll solve for in this class. We're going to learn more about those later, which are called repeating zeros. This really isn't considering certain types of repeating zeros. It's considering the ones that pass all the way through, not just the ones that that just touch the axis. So this is for ones that pass all the way through. We're going to kind of obsess for a while in this section about zeros, about how to solve for them, about when we have them, and that kind of thing. That's why this section is called Topics in Theory. So the first thing we look at, if you turn to the next slide, slide 3 in this PowerPoint handout, it says, please show that the polynomial function defined by p of x equal to x cubed subtracting 2x squared minus x plus 1. Please show that this polynomial has a 0 between 2 and 3, a real 0. So if I want to show this analytically, we could use the intermediate value theorem, like we just discussed, and substitute in each of these x values. So first I'm going to say the polynomial with 2 subbed in, and the polynomial with 3 subbed in. Hey, Elizabeth, we're going to get my calculator real fast. Okay, so when we put the 2, into this polynomial everywhere, analytically I can show you the work, which is substituting in this 2. We end up getting an output of negative 1. Whenever I substitute in an x value equal to 3, we get an output value, or a y value, of 7. So what we see here is, yes, there is a sign change. What this means to us is there must be some zero in between these two x values. We're not saying where the zero is. We're simply saying that it did happen, in fact, between these two x's. This is a similar function to something your calculator might use when it's asking you left bound and right bound on a zero when you're trying to use the calculator to find your zeros. So I'm going to say here, yes, sign change. So there must be a zero between x equals 2 and x equals 3. That's a pretty basic concept, I think, but it is something worth noting. So what I would like for you all to now do is to please try the now you try on your own. And if you have questions with the outcome that you get as you work this out, please be welcome, or please come by and ask me for help on how you would interpret your answer. Moving on now, the next concept we care about is actually not just wanting to know, is there in fact a zero between two x values, but more, can I manually divide out values from within my polynomial to find roots so that I can solve for all of the x values that help my polynomial to be equal to 0, all of the zeros that would satisfy setting my polynomial equal to 0. So as you turn in your PowerPoint now to slide 5, you're going to see a slide about division of polynomials. And you'll notice immediately that you have a nice labeled picture here where we see the top part of our fraction, the numerator, being a polynomial of degree 3. The PowerPoint is illustrating that the top numerator is called the dividend because that's what we're dividing into. And the bottom piece here where we have x minus 3, this is called the divisor. The idea is that we can divide these two things to try to extract out an x minus 3 as a factor so that we can then simplify this hopefully into an x squared, a degree 2 polynomial, so that we can solve for the rest of the zeros. Please note, before we even start our long division, so our goal here is going to be long division. Please note that it's possible to not have a perfect root or a perfect factor whenever I'm dividing. For example, what I'd like you to do for a moment here is recall with me back to when you first learned long division. So for example, if you had something like 201 as your dividend, no algebra here, just plain arithmetic. And let's say you were dividing into that a divisor of 5. In this situation, we would start off by saying 5 into 20 goes 4 times. Now, what I want you to do here is watch the pattern very closely, and we're going to try to make some connections between what you've done in the past with your arithmetic and what you're about to start doing now with your algebra. So we get 4 here. Then we have to go back and say, okay, well, 4 times 5 gives me 20. We then subtract. This is huge. We see that these numbers cancel. We bring down the next number of 1. 5 times what will give me 1? And at this point you probably say, oh, nothing. So 0 times 5 gives me 0. So in this situation we get a 1. At this point, normally in math, you would either put a decimal and keep adding zeros and dividing, or you would go ahead and stop and say, you know what, I've got a remainder here of 1. If you wrote this in fraction form, you would write 1 divided by 5. You always use the number that was your divisor on the bottom of your fraction. Now another example that we can look at to help us further establish some patterns that we've seen before Could be an example like 4 into 200. Here we would start off the same way as before, where we would say something like, okay, well, 4 goes into 20, how many times? 5. 5 times 4, multiplying here, gives me 20. We would subtract just like before. Notice that pattern again, please. The 20s cancel, 0 comes down, and we would then say that 4 times 0 gives me 0 back. So here we have no remainder. The idea here on this one is that 20 can actually be rewritten as 50 times 4, where 50 and 4 are both considered to be perfect factors. Now, on the original recall example that I gave you all, it is true that 201 can in fact be written as 5 times 40 and 1/5. However, hopefully you all remember that this situation, we would not generally think of a number like 40 and 1/5 multiplying by 5 as actually being good factors. They are factors, but they're not really the type of factors that we're looking for here. We're looking for whole number or even integer value factors back when we were doing arithmetic, when we were discussing this idea of factors. So please extend this idea of factors as we come back over now to the division of polynomials, because this pattern of wanting perfect division with no fractions or decimals is going to continue as we start looking at this algebra. So here with this example we have, we are supposed to be observing how to do long division. So the first thing I want you to note is that this dividend that we have on top here is not properly adjusted. When doing long division, we want the powers to count down from the highest degree that we see, not skipping any powers all the way down to to a degree of 0 on the final x, or a power of 0 on the final x. So for example here, I would say 3x cubed. And since I don't have an x squared, but I'd like one, I'm going to say that we don't have any. I'll put 0 x squared. Then I'm going to say subtracting 2x, since we have that term, plus 5. So again, I added 0 x squared so that my terms would be adjusted properly. The same thing holds for my divisor, x minus 3. I want to start with the highest degree that I have, which is a 1 here, or the degree that I have, the highest power, which is a 1 here, and I want to count down. So please notice this one is already properly adjusted, as we have a power of 1 on x, and then the negative 3 represents a power of 0 on x. So it counts down fully, not missing anything. Okay, now as we divide, we will be using x as our lead piece. So I'm going to ask, x times what will give me 3x cubed? That would be 3x squared. And just like before, over here with this multiplication, where we would always go back and multiply, we're going to take this piece and multiply. We're going to say 3x squared times x is equal to what? And the answer would be 3x cubed. The different thing, the new piece here, would be that we actually need to also multiply 3x squared now to negative 3. So we'll say 3 times negative 3 is negative 9x squared. Now we go back and we subtract, just like we did over on the right-hand side. Notice the pattern here, guys. When I subtract, what I recommend doing is actually going through your terms and just manually changing the sign, but circling it, so that when you proofread your work, you will remember that you've made the change. So here I have 0 plus 9x squared. That gives me positive 9x squared. I'll bring down the next term, negative 2x. And then we ask again with that leading x. X times what is 9x squared? That's a positive 9x. Multiplying back through, the 9x times x is 9x squared. And then 9x times negative 3 will be negative 27x. Once again, we are going to subtract, so we'll go back and change our signs. Guys, I recommend that you do not just write the opposite signs as you go. I've seen a lot of students make mistakes through the years. by doing that because you switch one in your head, but you accidentally don't switch the other. Take the extra 2 seconds to write the terms the way they actually would be, and then go back and negate those terms. And again, I use circles so I can look and remember that I changed both of my terms. So here we have positive 27x minus 2, or subtracting 2, we're going to have 25x. Bring then our next piece of positive 5. So now x times what is 25x? That is positive 25. 25 times x is 25x again. And 25 times 3 is going to be, let's see, it's actually a negative 75. Whenever I subtract this, however, it's going to change all of my signs. So it will change this one to a negative, and it will change my 75 to a positive. That's going to give me 80 as my remainder. So the answer here for this first example is going to match what you're seeing in your PowerPoint. We are getting a quotient polynomial of 3x squared plus 9x plus 25 plus a remainder piece, which is the fractional part of the quotient, where you take that remainder of 80, and just like we saw on the right-hand side with those recall examples, we take 80 and we put it over our divisor, what we were dividing by. So that's x minus 3 in this case. So that's what we get via long division for the first example that we've looked at. Now guys, again, I want you to notice, please, that in real life, conceptually speaking, this has not offered us a lot of information because our real goal was to get something a little more like the example where we were dividing the 4 into the 200, where we saw perfect factors here. We were very happy in that situation. Not so much when we had the remainder on our data, or on our factors. So this one is not really as useful. We would definitely not take this to the next step conceptually. Please turn with me now. The next slide actually had space for you to write that, but I wanted you, since you're taking notes with this, to be able to see the example on the PowerPoint that I was working through. Please now turn with me to slide 8, where we have another division example. Again, I'm skipping the you try it so that you have something to try in your notes. So actually I'll put that you should try, now you try, so that when I check your notes, you've got that in your notes. After completing the you try, we are on example, let's see, it's on slide A, another long division example. With this one, we have 5x cubed minus 6x squared minus 28x plus 8. So we can see here that the terms are all properly adjusted. So we don't need to add any space holder terms here like we did before. Okay, so now we're dividing in x plus 2. Again, x will be our leading piece. I'm going to make that a little bit more bold for you in your notes so that you can remember that's the leading piece that you use. Okay, so x times what, looking at our first term, will give me 5x cubed, x times 5x squared. Then we take that back to both pieces. 5x squared times x is 5x cubed. 5x squared times 2 is a positive 10x squared. We're going to subtract, and what we'll do here is we're going to change both signs. That makes our first two pieces cancel, and we get negative 6, negative 10, giving us negative 16x squared. Let's bring down our negative 28x. And now we say to ourselves, okay, x times what will give me that first piece, negative 16x squared? And the answer would be negative 16x. When I multiply that back, I get negative 16x squared, and I get negative 32x. Whenever we subtract this, it's going to go back and change both signs, which is good. It does make the first two cancel. And then we end up with 32 being positive and a negative 28. That is a positive 4 x. We bring down the positive 8. X times what gives me 4x? We're going to say positive 4, so 4 times x is 4x. 4 times 2 is positive 8. Here we're going to subtract, changing both terms. Notice again I'm still circling to illustrate when I go back later to proofread my work that I have changed the signs. In case I've made a mistake, I can catch it easily that way. And look guys, here we're getting a remainder of 0. This is wonderful. In fact, conceptually, this means a lot to us. So let's see. Our answer will still be the quotient polynomial that I have just now circled for you. The 5x squared subtract 6x plus 4. However, conceptually, what you are supposed to be picking up on this time through the course, because I know a lot of you from algebra have seen long division, the conceptual connection here would be that our original polynomial has now been rewritten in a simplified way that would allow me to solve or allow me to continue on towards solving for zeros of a polynomial that I could not solve any other way, at least not analytically. So with this right here, I have now split this into my original piece, which was x plus 2. We got that because that was our divisor. And the other piece would be the quotient that we found when we were dividing. The 5x squared subtract 16x plus 4. That's what we actually just now discovered, which is huge. Because again, guys, now you could try to either factor this one further, or you could use, or if it were not factorable, you could choose to use the quadratic equation, or perhaps completing the square. But the idea is that if this original polynomial had been equal to 0, you could now finish and solve for all of those zeros. And guys, as we go through this material, you're going to find that not only does it make you feel really skilled to be able to do this by hand for powers that are now greater than 2, for degrees higher than 2, but that you can also now solve for things that even your graphing calculator could not solve for, like imaginary zeros. So this should be actually a pretty huge idea to you. So now that we have reached this wonderful connection, let's talk about two theorems that are very useful and actually quite similar to one another. So I have now skipped past the you try it, which again, make sure you try all of those in your notes. I'm not going to keep writing that. I feel like that uses too much video time. But as far as the theorems we have the remainder theorem, and we also have the factor theorem. And this is on slide 10 if you are following with me as you're taking notes. Slide 10 of your PowerPoints. Okay, so the remainder theorem, if hopefully you're either reading in your book or you're looking at the PowerPoint online or on the paper that you printed off. But the remainder theorem basically says if a polynomial p of x is divided by x subtract k, the remainder is equal to p of k. So p of x divided by x minus k gives me a remainder of p of k. The factor theorem builds on that by saying even more. It now says the polynomial p of x has factor x subtract k if and only if, when I substitute in that number, that k, the polynomial is equal to 0. This right here is actually the really, really huge part of these theorems. This is very good for you to know this. So p of x, if it has factor, so whenever you divide x minus k, it is a factor. A perfect factor if the remainder is equal to 0. So you guys see that we say here p of k is equal to 0 because that's equivalent to saying the remainder is equal to 0. Since we just now established over here on the remainder theorem that whatever p of k is equal to happens to be the remainder. So here's the idea. Let me give you a little sketch. The idea is that we have some polynomial, okay? And as we're looking at this, let's pretend this right here is number, I don't know, let's say 4. X is 4 right here at this x-intercept. So the idea is that given this P of x that I've just now sketched for you, if I go on here and I say substitute in x equals 4 into my polynomial equation, well, you guys can see graphically, I hope, that right here, y is equal to 0 because I have an x-intercept. It's crossing the x-axis. So P at that value, my function's value when I plug in the x, is going to be equal to y at x equals 4. That's what that notation means. It's going to be equal to 0. Again, a further connection is that also meant that when I divided, my remainder was 0. So this goes both ways, guys. If we use these theorems to check before starting problems, if we substitute in, so if we try possible zeros by plugging them into our polynomial, to see if the remainder is 0, which also means to see if we do have a 0, then we don't waste our time with division. We are able to only spend time dividing out perfect factors. Which means as we take our original P of x and we start breaking it into these things being multiplied by each other and setting it equal to 0, we'll then be able to use that zero product rule that we learned about this semester that says we can split them into two separate equations and solve. So it allows us to finish problems more efficiently without manually dividing out every possible value. So on slide 11, you see an example that says, please use the remainder theorem and synthetic division to find P of -2. So the first idea, first we're going to do part 1 of this slide right here. It says, please test into my polynomial. Let me put the equation here on the paper. Please test a value of x equals -2. So again, the idea is that everywhere that we have x, we'll be putting in -2 to check and see, to check and see if in fact this has a remainder or not. So what we see here is that we end up with -1 after substituting in -2. Now guys, if you have trouble with substituting and remembering to put parentheses around those negative signs, if that confuses you, remember that you can use your calculator by putting your polynomial into y1, that equation, and then you can actually use either your graph or you can use vars, the vars choosing the y1 of function notation on your main screen, like we've talked about in class. So we get a -1 here. What does that mean? It's actually kind of unfortunate because what that's telling me is that if I divide, my remainder is going to be -1. Now the directions on this particular problem are telling me to divide. So we are going to go ahead and try out a new form of division called synthetic division. However, conceptually speaking, we would have usually have known to go ahead and stop here. We would not choose to keep working usually. But for the sake of fun, let's go ahead and divide this out and see what we get. So, you know, guys, you've looked at some long division here. And the interesting thing is that for every example you've seen so far, you actually could have done synthetic division as well. The way synthetic division works is it is always allowed, so I'm going to say you can use it, if your divisor is of the form plain x, so no power, no exponent on x, no coefficient on x, and you can have plus or minus really, x plus or minus some number. If your divisor looks like that, so as you go back through your notes, please notice that every example so far has been of that form. If your divisor is of this form, you are actually also allowed to use synthetic division, which I think you all are really going to like. So here's the way it works. Using synthetic division, I will always take what x is actually equal to. So in this situation, let's see, we have -2. Again, remember that the significance of -2 is that is my proposed zero. I'm trying to divide it out so that I can now hopefully factor out another piece. We know it's not going to factor because, again, we know there's a remainder, but I want you to understand that's why it's a -2 right there. I also want you to remember, guys, that if I had put this in factor form, we've noticed in class that there is an opposite connection. So if I had put this in factor form, it would have looked like x plus 2. Remember. Because an x plus 2 set equal to 0 gives me a solution of x equals -2. I want you to remember this, guys, because x plus 2 is what you have to use for long division. So don't forget that, okay? Now, as we go into the synthetic, we're using the -2. We also have this polynomial, -x, let's see, I'll write it up here at the top so you have it. P of x is equal to -x to the 4th plus 3x squared, subtract 4x, subtract 5. So we have this polynomial. We see that the degree of this polynomial is 4, and just like with long division, we need to adjust this polynomial. So let's go ahead and rewrite P of x so that we are not missing any terms, so that we start with our highest power, our degree of 4, and we count down, not skipping, for example, like we did here, that x cubed. So -x to the 4th and 0x cubed, and we have 3x squared, subtract 4x, subtract 5. So now we have adjusted our polynomial, and we are ready for synthetic division. I'm going to write that -2 down here again. And now we write our coefficients only. -1, see how we had a -1 right here in front of x to the 4th, so -1. Then we're going to write our 0. Then we write our 3. -4. -5. If you are taking notes, which I hope you are as you watch this little tutorial, I recommend that you stop taking notes for just a moment and that you actually watch this process, okay, because it actually happens very quickly. I will repeat it 2 times, so I'm going to say it again out loud after writing through it 1 time. So make sure that you're just watching right now, please. So again, we have this -2 because that is my proposed x equals 0, or my x equal number, okay? It's the opposite of what I would have used in long division. Notice also we got these coefficients off of our adjusted terms. And now what I'm going to do is drop down -1. And I'm ready to begin. This goes very quickly, and it's a series of multiply, add, multiply, add, multiply, add, until I get done. So first I say -1 times -2. I'm multiplying here. -1 times -2 is +2. I'm going to add these two down to give me a 2. Then I say 2 times negative 2 is negative 4. I'm going to add down here to get, let's see, 3 plus negative 4 is negative 1. Then I multiply. Negative 1 times negative 2 is going to be positive 3. I will add and get negative 1. Negative 1 times negative 2 is going to be 2. And here I'm getting negative 3. Okay, I actually made a mistake here, so please correct your notes. I thought something didn't look right since we already knew from the previous little testing the remainder theorem exercise that we expected to have a remainder of negative 1. So I took a second to proofread what I had just written, and I bet some of you guys caught it. When we were multiplying here, let's see, we said negative 1 times negative 2 is positive 2. Then we said 2 times negative 2 is negative 4. We put those together to get negative 1. Negative 1 times negative 2. Right here I made a mistake. Please correct your notes to say 2. Negative 4 plus 2 is a negative 2. And then negative 2 times negative 2 is a positive 4. Then when you put those together, we are getting the expected remainder. So let me write this one more time so that you've got it done correctly in your notes. I don't want this to be confusing you. And I will try to not make any multiplication mistakes. So let's see. Also, this gives you an opportunity, if you were watching before, to be able to actually take notes this time. So as we look at this right here, we're going to drop down the negative 1. Negative 1 times negative 2 is 2. Put these together to get 2. 2 times negative 2 is negative 4. Put these together to get negative 1. Negative 1 times negative 2 is a positive 2. Put these together to get negative 2. Negative 2 times negative 2 is positive 4. Put those together to get a negative 1. So here we've done our synthetic division. Let's remember that negative 1, first of all, was the remainder. Another pattern that you may have noticed with your long division is that your starting power is always 1 less than your initial power or your initial degree. So here we had x to the 4th on our original problem. That means that here we're going to start with x to the power of 3. You always start 1 less because you divided out one of your x's. Well, 1 less if you are dividing out an x to the power of 1. So it's always going to be kind of like subtracting that number of x's that you just divided into it. So we had x to the first going in with that x plus 2 that we hypothetically just now divided into it that would have gone to the negative 2. That means we're starting with a cubed since 4 minus 1 is 3. Then we count down. 3, 2, 1, none. Meaning that we have negative x cubed plus 2x squared minus x minus 2 and negative 1 over. At this point, you must remember that the factor that went with negative 2 was again x plus 1, because when you write this in fraction form, it is x plus 2 in your denominator. So this right here is what I got when I divided using synthetic division. And again, we knew that the remainder had to be negative 1, which in this case proved very useful for us because we were able to prove ourselves. Again, we're not particularly happy beyond just learning how to do synthetic division because we can't go any further with this. We're not able to actually solve this polynomial equal to 0 because the fraction is messing us up. Let's see, so some things to note. Now that you've learned synthetic division, remember that you can only use it if your divisor, like we said before, is a plain x to the power of 1. However, long division, you can always use. So this is why you learn both methods. In this class, if you're able to use synthetic, I would recommend that you do. For slide 13 and slide 14, where you're supposed to be substituting in those x values to see if p of x is equal to 0 or not, that's going to be part of your homework. So please complete slide 13 and 14 on your own in your notes. Basically, you're just substituting in x values and you're telling me, is the polynomial equal to 0? The connection here is if the polynomial is equal to 0, then you just found yourself a 0. On slide 15, we start with a very similar example to the one that you were just now trying on your own from 13 and 14. It says, determine whether the second polynomial is a factor of the first. So here we are given p of x is equal to 4x cubed plus 24x squared plus 48x plus 32. And we are being asked, is x plus 2 a factor? And by this, of course, we mean a perfect factor, not can we write it as some kind of quotient with a fraction attached to it. We want an actual perfect factor on this. So again, we're going to use our previous two theorems. So we need to plug in the 0 that would go with x plus 2. So remember the opposite of x plus 2. You know, the number that I would get when setting x plus 2 equal to 0 is x equals negative 2. So we're going to use x equals negative 2. So here we'll say p of negative 2 is equal to 4 negative 2 cubed plus 24 with negative 2 squared plus 48 times negative 2 plus 32. After putting in negative 2 in place of every single x, we are getting that p of negative 2 is equal to 0, which is good. That means that yes, x plus 2 is a factor. So in this situation, we actually have a 0 that we would like to divide out of this polynomial. Now, let's move ahead. I'm again leaving you all the you try it, which is slide 16. Let's move ahead now to slide 17, which kind of starts to put all of these pieces together for us. So on this one we have p of x equal to 2x cubed plus 5x squared minus x minus 6. And part A of this example says, show by synthetic division that negative 2, negative 3 halves, and 1 are zeros of p, and then write p of x in factored form. So part A says this that I'm writing. I'm trying to write it out for you. Hopefully you still have this in front of you, or you're probably going to be missing a lot of your visual learning here. So show by synthetic division that these are our zeros. And then part 2 is again write it in factored form. So what I'm going to show you guys how to do is how to take synthetic division and how to fully extract all of those zeros by dividing, then dividing on what you just did, then dividing on what you just did. So this is going to take the previous work and keep working on it until we get down to a fully factored polynomial. So first we'll use x equals negative 2. Coefficients here are, let's see, 3, 2, 1, none. Everything's fully adjusted, so the coefficients are 2, 5, negative 1, negative 6. When we drop this down, we have 2. 2 times 2 is negative 4. 5 minus 4 is 1. 1 times negative 2 is negative 2. Negative 1 and negative 2 is negative 3. Negative 3 times negative 2 is positive 6, giving me that remainder of 0. The last piece, the last number you get is always your remainder. Also, guys, remember here we have a power of 3. So it's going to go down now to x squared. I'll put an and between these two terms. So it goes x squared, x, and then no x. So that's the first piece I got. Conceptually, what we just now found is we got that this original polynomial, 2x cubed plus 5x squared minus x minus 6, we got that the first factored piece of it is x. Now, instead of saying x subtract 2, the opposite is actually x plus 2. Remember, when you put it into parentheses, it's the opposite of what you would have had when it was just solved for x. So x plus 2. Then we're going to take our bottom stuff here that we actually got when we divided, 2x squared plus x minus 3. So we have taken our polynomial and successfully broken it into two factors using synthetic division. Now let's use our answers from synthetic. Let's use the coefficients on this little polynomial we just wrote, the 2, 1, negative 3, to continue dividing. So here we're going to use 2, 1, negative 3. We are literally using the numbers right above it. I deliberately kind of pushed those numbers to the side so you wouldn't think it was just one long thing. And then I'm going to use negative 3 halves this time. Here we drop down to 2. Let's see, 2 times negative 3 is negative 6. Divided by 2 is going to be negative 3. Let me check my math since it's hard to talk and think at the same time. Negative 6 divided by 2 is 3. Yeah, okay. And then we have 1 minus 3 is negative 2. So there's a 3 times 2 is a 6 divided by 2 is going to be a positive 3, giving me a remainder of 0. Again, the power before was a squared because we're using the one directly above. So now I'm starting with an x. And what it means conceptually over here, we would have kept our x plus 2, but now we have broken the squared piece into x. And the negative 3 halves, remember, will become positive 3 halves. And then our other piece so far is 2x minus 2. Okay, we have one more piece to check. Now we're going to check 1 using synthetic division. And not only are we checking, but we're actually factoring here. So now I'm going to use the little linear equation we have, that 2x minus 2 that we have from directly above where I have just written the 1. So now I'm going to use 2 and negative 2 in synthetic division. So we have 2. 2 times 1 is 2. When I subtract, I get a remainder of 0. And of course, since I had a power of 1 on that x, what that means is I just get a plain 2. So this has now been broken into two pieces. Let's see, I divided in a 1, so that means x, the opposite of positive 1 is negative 1, so x minus 1. We just now got 2 as our solution when we divided that in, so we have a 2. And then we still have all of the other pieces that we just got earlier via our division. So right here we are looking at p of x fully factored. And to get there, we used our synthetic division like Part A requested on this you try it exercise, or excuse me, on this example exercise. Now for Part B of this example, we are being asked to graph this p of x in a suitable viewing window and locate the x-intercepts. So the idea is that we can actually look at the picture and hopefully understand that the x-intercepts had better be the exact same spots that we found in Part A. Also, using some of the things we've learned before, please notice the 2 in front of x squared, or excuse me, please notice the 2 in front of x cubed. That means that my polynomial is pointing up overall. We can also see here a power of 3, or 3 is our degree, on our leading term. So what this means, again, we said the 2 meant up overall. And now that we're looking at this 3, we know that means up to 2, curves. And we already know that our zeros are at x equals 2, negative 3/2, and 1. Wait a second. I just skipped examples on accident. This is the you try it for you guys, so I just now helped you start yours. That's your you try it. That's for you to do. Let me get back to part B of the one I was actually doing. My PowerPoint got out of sequence. It does make a difference when I'm graphing this because it's slightly different. On our polynomial, we have 2x cubed plus 5x squared minus x minus 6. So there's some different characteristics there. And the zeros that we just divided out were for x equals negative 2, x equals negative 3/2, and for x equals 1. So again, as we look at this, there are some similarities, which is why I didn't catch it right away, such as we do still see up overall. We also still see up to 2 curves. So as we draw a sketch for this, and again, as you all check this in your graphing calculators, and since this is really more of a graphing exercise, meaning that technology is okay here, as we graph this, I should be able to get a pretty basic picture, perhaps not as good as what you might get in your calculator, but a pretty basic picture just from those main characteristics that we have learned in class. The up overall, the 2 curves, oh yes, and of course don't forget the y-intercept part. So I'm going to kind of start this picture backwards. I'm going to start first with my zeros. So I know there's a 0 at negative 2. So I'll put a dot here for my x-intercept at negative 2. I also know there's an x-intercept, or a 0, at negative 1 1/2, which is right about here, kind of close to negative 2. And there's another one at 1. So I have 3 zeros. Next, I always start on the right-hand side and kind of sketch backwards when I'm doing these by hand. So next we look and say, okay, well, it's going up overall. So I'm going to put an arrow on the right-hand side pointing up. Let's see, we also know it's going to cross at about a height of negative 6. So something like this on the y-axis. So as I sketch this, I know that the polynomial has passed through the x-axis, and it's coming down to about negative 6. Now, on your calculator, if I recall correctly, you're going to see a vertex near here, right around y equals negative 6 at that x equals 0 point. That's not required, and we don't really have a way without calculus right now in this class to figure out exactly what the vertex is. We haven't learned anything like that right now. But a rough sketch will show that it's crossing. We just don't necessarily know analytically if it's going lower or not right now. The graphing calculator does show us the vertex, though. So I'm going to go ahead and turn it around, make it start going up. We know it has to cross through this point. We'll talk more about why we know it's crossing, not bouncing, later in this chapter. We pass through that 1 1/2, and then, of course, it needs that second curve so that it can come back and pass through negative 2. So we're getting a picture kind of like this. And again, the significance is that these x-intercepts that we just now divided and found on factored form, that's exactly when we have zeros, x-intercepts, on our picture. Now, the last part of this equation, part C, says to solve the polynomial equation equal to 0. So we have this exact same polynomial, and we're being asked to solve it equal to 0. So let's see, when we factored this a second ago, we found 2 being multiplied by x plus 2. I put the 2 in front on purpose just because I like to put it there. And then we said x plus 3/2, and we also said x minus 1 equals 0. That was the factored form. Hopefully everyone's starting to see some really cool connections between those zeros that we divided out, that picture, and now the factored form if we had been told initially to solve this thing equal to 0. Because we would have said x plus 2 equals 0, x plus 3 halves equals 0, and x minus 1 equals 0. And of course, that 2 divides off. If I divide by 2 on both sides, it just goes away, remember. Because 0 divided by 2 on the right is just 0. So the 2 canceled off. But then we end up with that negative 2 that we've already found. We end up with that negative 3 halves that we've already found as a 0. And we also end up with that positive 1 that we found. So hopefully that's pretty cool. That all three things, all three parts of that problem are literally connected. They're basically the same thing. Okay, we have 2 more examples, and that will be everything that I'm going to talk you through for this section. So thank you for your patience in watching this video. The first example is on slide 19. It is asking us to divide 6x squared plus 5x minus 10 divided by 2x plus 3. Now here's the deal, guys. We know that technically we can't use synthetic division because there's a 2 attached on this x. X is not allowed to have a coefficient other than 1 or a power other than 1. So we need to go ahead and use long division. Long division is required. So as we do this, let's see, every term appears to be adjusted. We'll say 2x plus 3 dividing into 6x squared plus 5x minus 10. And we'll follow the same thing that we did at the start of this lesson. 2x times what is 6x squared? Excuse me, that's a 3. Please fix your notes. 3x. 3x times 2x is 6x squared. 3x times 3 is 9x. We'll go back and subtract this stuff by changing this to a negative, this to a negative. Then we're going to get negative 4x and bring down our negative 10. Now we say 2x times what gives me negative 4x? That's going to be times negative 2, which does give me negative 4x. And negative 2 times 3 gives me negative 6. So here we get, whoops, I have to change my signs. That's me trying to get into a hurry. That's bad. Okay, so now we actually get negative 4 as our remainder. And negative 4 over 2x plus 3. So our answer here, as far as division alone is concerned, is 3x minus 2 and negative 4 over 2x plus 3. Let's look at one other example where long division is required. And that's just to make sure that while we have done some synthetic in here, that you guys can still handle long division, because sometimes you'll have to do it. So in this example, this is slide 21. We have 5x cubed minus 4x squared plus 7x minus 2 divided by x squared plus 1. Please notice immediately that that divisor needs to be adjusted. So the x squared plus 1, that's what we're dividing into the other part, into the polynomial, needs to have 0x added to it, just to kind of clean up the process. If you forgot and you were very careful, you'd still make it through the problem, but it does make your work cleaner. So now we're going to put our 5x cubed, subtract 4x squared, adding 7x, subtracting 2. And again, we're using x squared as our leading piece, just like always, using that first leading term right there. X squared times what is 5x cubed? We have 5x. So that gives us 5x cubed back. Now 5x times 0 gives me and 0x squared. 5x times 1 is plus 5x. Now we're subtracting everything, so go back and change all of your signs. Let's see, these first two pieces cancel. We have negative 4 minus nothing, which is still negative 4x squared. We have 7 subtract 5, which is going to be plus 2x, and we'll drop down our negative 2. Now we say x squared times what gives me negative 4x squared. That's a negative 4. Multiplying that back through, we get negative 4x squared and 0x minus 4. Now when I go back through here and change all of my signs, we end up with 2x plus 2 as my remainder. So basically we have here 5x minus 4 and 2x plus 2 all over x squared plus 1. Okay, that's it for section 3.6. Please work out all of the you-try-its and let me know if you have questions.